collectively. To your discretion. They will aid in any discussion that you have if you go to the experience. It's not feasible, and it's something that we did not ask people to present in the past. People did present all their data in the past, which was fine, though we did not ask them to like synthesize like 135 plots with the calculations. You gotta pay attention to the back of the make sure.
This video location, we find, for example,
Let me open this up.
we find the resistance, right? The issue locations. Then, for every location, there's two resistances.
Yes. Three.
Basically, we have like 10 resistances you have to find. Right, if you do that. And then on top of that, you have sheet resistance. Yeah. For each one. Oh, yeah. Right? What is that going to make it? So you have, right now you have 3 values to the side. Fusion. No, hold on. You have the fusion of poly.
You guys will have a little bit of extra time to present today for each of the groups, like 15 minutes or so with some questions. I don't think we're going to be doing any, we're not going to be adding content for the final, right? This is more for the final group presentation, and Dr. Gotzi, hopefully, he has a very nice presentation of like a system integration example that he did for his postdoc work, which was like really cool. If he has the slides, it'll be great. I don't currently have them. Very good. And we can answer questions. Hopefully, if you're asking for that extension, you can ask it. I'm less sure how he will do it. The compromise might just be turn in what you have for the homework and we'll grade accordingly.
Hey Justin.
Yes.
Do you know when the midterm or not the midterm, the final review is?
So I'm gonna. Yeah, we can figure that out now between us. So I was going to propose to do the final review Tuesday at 4 or 5 p.m. It's only going to be like an hour and a half. So we'll just run through the material and I'll do a couple examples.
When is that?
Tuesday. You
The
can
exam is
choose.
Wednesday, right?
The exam is Wednesday at 8 a.m.
Yeah, okay.
Can we do early Tuesday?
Maybe earlier Tuesday.
Yeah.
So Tuesday, the earliest I can do it on Tuesday is like 2, but I didn't want to bother if other people had exams. I don't know about the overlap with exams.
Tuesday is reading day.
I don't know what reading days are. Okay. Okay, good. Never mind. Okay, so I can do 2. That's okay. That's about as early because I have to do some stuff that morning. I have meetings.
When are the lab reports 1 grades are coming?
Hopefully tomorrow.
Hello, everyone.
I'll post them.
Hi, Professor.
How are you?
Exhausted.
Exhausted. Oh, it's the end of the semester. Like your backpack.
Thanks.
Okay.
Professor, can we have the extension on the homework, please?
Or that. We'll talk about it in a minute. Let's not start the whole thing with extension. Okay.
I have to change the view.
What is it?
Change it to the desktop. Looks like it's on the overhead camera.
Did we change it? Okay. you know?
Yes.
Okay, so that's the first group. Bokar, Joseph, Chester, you all are here? Okay, please, come up front. Okay, so here's what we're going to do today. We're going to go through the last two group activities. And then we're going to talk about exam. We're going to talk about lab reports. And we're going to talk about what a great opportunity this has been for us to work with you. This is our last lecture. And that's where we're going to end. Okay? So you have about 15 minutes, longer than other groups because there's 3 of you, and 5 minutes Q&A, and then you start with the next group. Okay? Packaging is so important. You could have not 1 course, but 3 courses on that.
Yes, that was the thing that we got into actually.
Now, before you start, the rule of thumb is, and I want all of you to understand, hopefully those who are going to go into the hardware, you always design the package at the same time with the electronics and the chips. If you design the package at the end, the 100% guarantee that you fail.
Yeah, we're actually going to go over that too.
Yeah, remember that. Okay? This is a golden lesson I learned the hard way. All right? So take it with a lot of, values. Okay, go ahead.
Ready? All right. Good morning, everybody. So by now we've all been through the fabrication process, which is basically getting the wafer from the starting point all the way to the end, putting all those devices that we want on this wafer. So at the end, we're going to have to somehow find a way to utilize these devices. So the way to do it is by using IC packaging. IC packaging is basically the final step of the fabrication process. What it does is basically it provides a housing unit for the dies that are on the wafer. So the purpose of it has 4 purposes. The main one is provide electrical connectivity to the outside devices. So you somehow have to find a way to connect these transistors to the outside devices that you want to connect them to. The other thing is for physical protection. We all know that these devices are very fragile. I mean, we've all tested it on a microscopic probe, how easily they can get scratched. So that is another purpose of IC packaging. Another package is for environmental protection. Let's say if we have electromagnetic radiation or something going on, it's going to protect it from that as well. Another thing is heat dissipation. That's another purpose of IC packaging. So
you have materials, you have electrical, you have mechanical, you have thermal, you have long-term reliability. It's a whole interdisciplinary approach on its own.
Absolutely.
Right?
Absolutely. There's a process to making. There's a process that you have to go through for IC packaging. But before we get to that, we have to go through the pre-packaging process, which is a 2-step process. The first step, you grow a passivation layer on top of the layer, and this layer can be the usual stuff: silicon nitride, silicon oxide, or polyamide. And this layer is basically to protect the circuits. And when we do that, we leave the electrical contact exposed. I'm going to explain about why. And the reason for this is basically the second step, which is basically the sorting process. We're going to isolate. We're going to have to isolate the good and the good and bad dyes on the wafer. Go to the next step. So this is the whole packaging process. We have to go through these processes in order to get a complete package. The first one.
But we are doing this in the context of electronic chips.
Yes.
Right?
Yes.
Because this whole recipe changes dramatically
Absolutely.
for some other applications.
Absolutely.
Right? Some of them will stay the same, but it doesn't necessarily follow the same order.
Yeah, we have a slide at the end that basically goes through this. So this is the packaging process. So the first one is backside strip. So The backside prep is basically the backside of the wafer. What we do, the wafer thickness can affect the steps that follow, which is basically the die separation and packaging. So we're gonna have to reduce the thickness to approximately 100 micron, and the technique that we use is chemical mechanical polishing that was discussed by the other group. When we do this, we have to make sure that we cover the front side, the front side with a thick resist. The next step, after we prepare the backside, we are gonna have to do die separation. And basically what we have to do on the wafer, we separate each die by using a diamond saw scribe, using a P-pattern scribe line. And then after that, we have to pick and place the die. We have to identify the good dies from the sorting step. Now the sorting step is basically it's a process that's done. Each die is going to get electrically tested, and then the bad ones are going to get marked. So that is what the sorting step is. Basically, it's going to mark all those bad ones, and then once we pick the good ones, the next step we're going to go to die inspection, which basically we're going to be looking for cracks and defects on these die. And then after that, once we get and this step is being handled by an automated optical microscope. Once we're done with the die inspection, then we're going to go to the next step, which is die attach. So die attach was basically what we do. We pick the good ones and we put them on the package. And this can be done in two ways. One of them is conductive. We can use a gold silicon, or it can be non-conductive using an epoxy adhesive material. So this is basically a representation of what I just talked about. As you can see, these marks over here, these are the bad ones that was identified in the sorting process. This is the die separation. This is how the die separation works. And this is where the dies are picked and placed on the chip. On the package. And this is basically another representation of how this process works. And in the next step, we're going to be talking about the bonding, how the bonding is going to work. And I'm going to pass it down to my colleague. He's going to explain how that process is done.
Hey guys, my name is Joe. I'm here to introduce just some types of bonding that can go into IC packaging. Now, bonding is one of the most important steps in IC packaging. This is where the electrical leads are actually, or the leads from the IC are actually connected to the board. So one of the types of bonding I'll talk about is flip chip bonding, which is basically the reflowed solder is put onto the leads of the die, and then the chip is flipped, hence the name, and bonded to the package using the solder. So like hot air or heat is applied to melt the solder and establish the connections. This leads to much smaller chip assemblies because you can have much denser connections, and it's also since you're not really having wire, it's mounted directly to the board. That also reduces space as well. This leads to much shorter connections, which is higher speed and lower inductance. But one thing to take into account, the disadvantage of this might be that thermal expansion could occur. So you have to match the board to the you have to handpick the board to prevent that crack connections.
So this electronic chip needs to work at 110 degree Fahrenheit in Death Valley, okay, or 115, and it should also work in minus 25 degrees in Minneapolis, Minnesota, right? So that's what you mean by thermal variation,
Yes.
right? Because if any of them won't work, if any of your package electronics in your iPhone goes through some form of a cracks, that's the end of the product,
Exactly.
right?
Because you can't go back like you can.
Yeah.
I'll go into detail in another slide, but this is a type of surface mount, which means once it's done, it's done.
Yeah.
Right, you don't want to blow up.
Right.
So another type of bonding is tape automated bonding, and that is where electrical lead system is deposited onto a tape via sputtering or thermal evaporation. The tape is then stamped or patterned to make the leads to the actual the IC. The die is aligned, and the diethylamine bonded using a tool called thermal, which is basically like a hot press. It presses the, it actually forms the bond. And this is used for extremely thin device fabrication. I'll show that on the next step, just what I mean. So since it's pressing it down and establishing the bonds, that makes it nice and thin. And then here's another representation of the flip chip. So this is the solder which is deposited on the IC, flipped, and it establishes the connection right there, as you can kind of see it. I'm going to pass it
So
over.
if any of your layers that you put in to make your electronic chips and your transistors has exceeded the stress, remember we talked about stress, compression, and tensile, remember that halfway through the semester, right? If any of those intrinsic stresses, if any of those layers exhibited more stress than it's supposed to, guess what happens when you put the pressure for this flip chip bonding? Cracks, right?
Exactly.
So this is how the final product comes to realization. Because if you have not done your reliability tests at each layer, and if you hadn't characterized it, it's going to come and haunt you at the end.
Exactly. Just as Dr. Gatsi said, there's
Yeah.
a lot of planning that needs to go into
Right.
every single step. So my colleague Chester is going to take over when it
Sure.
comes to this.
Right. Hi, I'm Chester. And that comes to the pre-sealing inspection. You want to check the bonding is not missing, and also like the conductivity still works. And it goes on to sealing. The sealing I conclude in soldering or the encapsulation. The picture is from the textbook talking about the soldering. It goes over sputtering and patterning and plating, discum, nickel plating, solder plating, resistance removal, etching, reflow. It's pretty much similar to when we do the semiconductor. And I split final steps with two steps. One is inspection part, the other is the yield. And the inspection, mostly we generally do the defects inspection by optical inspection or X-ray inspection. The optical, you see the packaging in the visual light range, which find the defects in micro level. And it is faster, but it only can look over the surface. So some may require the X-ray inspection. It sees through the structure, so it has a high resolution, but it also takes those. But it can see through a metal to check like all the conductivity is work. And some optional inspection are reliability inspection. It contains temperature, pressure, stress, and humidity, and some more inspection wherever the company wants. And the other part is the yield. The yield equation is coming from the binomial distribution, and it's basically the explanation of the parenthesis negative d naught times A. And d naught is the number of defects divided by wafer area, and A is just the area of each dice. And we conclude the chip characteristics as the summary, as some of the process affected by the integration level, wafer thickness, chip dimensions, environmental sensitivity, physical vulnerability, heat generation, heat sensitivity. Those are something you have to be tested for the final inspection as well.
Right. So can you go back to your previous slide? I just want to point this out. The wiring steps that take place before you encapsulate the whole thing and finalize the product, that by itself is a field of study. Because when you bring this very thin diameter gold wire down, even when you use a robot, you need to make sure that it adheres well and it adheres permanently, and it could stand things like vibration, temperature differences, and other stimulus that or forces that could really detach it at any given time, right? So I just want to point this out that when people see robots doing this wire bonding, we don't use robot, by the way, in our research labs. We use what? very professional graduate students. Okay? What they do is the really first time that this is happening, right? So it doesn't make sense to have robot doing it, right? Robot is done for mass manufacturing, right? Not for research. But I want you to pay attention to this because you learn in this class as you're ready to put layer on top of another layer, what did we emphasize that needs to be absolutely what? Clean, residue-free, right? And we talk about techniques like oxygen plasma to remove those residues. Well, guess what? Same thing applies here. Because this is a thin wire, and you bring it and you absolutely clean. Yes?
It's an experience I've faced a couple of. So you think that it's connected, but after a little bit of movement,
Absolutely.
it just comes off. How can we sure?
You go through, there are techniques to measure the conductivity for each of this.
Yeah, but how? It might be connected, but it's not like.
Well, there are a series of, as I said, mechanical and electrical tests that they do in industry before they do the last layer.
Okay.
Because once you put this in, as he said, it's done. It's done, right? So you better make sure that these layers are tested.
And now we finish the process of packaging. We
Yeah.
go pass on to the each types of the bonding style.
So there's a bunch of different types of IC packaging styles. I'm just gonna go over a few briefly, just to give you guys an idea. So the first one I'll go through is dual inline packaging. So this is a through-hole mounting style. Through-hole means that it leads into a pin, essentially. These typically have rectangular housing. Everybody here has seen these. You put them in a breadboard.
I injured myself so many times.
These have largely been phased out due to the large size and the rise of the SMTs, which I'll go on the next slide. But with prototyping and breadboard circuiting, these still have a lot of use in the application. Another type is a pin griddling. So this is another through-hole style mounting style. Square, rectangular housing. You see these in your computer motherboards. These are most often mounted to sockets and pre-soldered
Yes.
to circuit boards. These allow for more connections and pins per IC than older packaging types such as the dual inline. And so I'm going to go through the SMTs, which I talked about on the previous slide. SMT surface mounting style, which means the package is mounted directly to the board. So this means the first one I'm talking about is leadless chip carrier. The name would suggest there's no leads, there's no pins. It uses metal pads at the outer edges. You can see right here to establish connection to the board. Due to the reduction in size and no need for pins, it's a lot more resistant to shock and vibration, and it's also lower cost. Like the pin grid array, the ball grid array is the surface mount variant. It's rectangular, has a matrix pin style pattern, as you can see. This is basically an improved version of the pin grid array. Much easier to automate since you could that's the whole reason SMTs have they're a lot better. And they allow for a lot higher density of the pins and thermal resistance between the package and the circuit board.
So this whole pin idea, when it started in semiconductor industry and for electronic chips, also has gone through series of evolutionary steps, right? As you know, you nicely showed two different examples here for flat electrode versus pin electrodes versus different arrays of pins. But where I'm getting at with this is that, in fact, when I look back, it's like 30 years ago, 35 years ago, it was these pins that inspired folks in my field, okay, to make those very narrow, tall microneedles by using bulk micromachining that you learned a little bit about, okay? Bulk micromachining, remember, removing the silicon through some form of a wet etchant, like KO etch. And And those tall electrodes ended up being like an array on a chip, okay? And enabled neuroscientists to do deep brain stimulation, okay? So today, the pacemakers that, believe it or not, they're installing in the brain to fight Parkinson because it stimulates the neurons every 2 or 3 minutes, uses those tall electrodes, right? So we went from this to that. Do you see what I'm saying?
Exactly.
So it's a really nice inspiration, and that did it. That inspired us to challenge ourselves to make those electrodes in a different way for a different application.
Well said.
Is this the last slide?
This is the last slide.
Well done. Well done. Great job. Great job. Questions?
I've got small questions. That's when you use the chips in your lab, many restrictions that we cannot apply a high current or high voltage that will hurt the chip. Which part of the chip will be hurt? Or why we are hurting? I know the large current will generate heat.
What is exactly the question? I didn't get it.
I mean, I think I kind of got it, but
Yeah. What is it?
I think he's asking about how the limitation of current that we can apply on
Uh-huh.
the chip,
Yeah.
right? I think that depends on that circuit. I mean, most of the
Yes.
circuits that we have, they don't have a lot of abilities. Like you can't apply high current.
Yeah.
If you go anywhere near, I don't know, maybe 1 milliamp or something like that, that circuit is gonna start to heat up pretty quickly.
So the current for these chips are normally very small, but also I think you point out an important issue here because in, for instance, power electronics, where they deal with high voltages and high currents, they have to worry about what you just asked. So they need to make sure that those pins won't melt the layers, right? Because it draws more current because of that application, right? So power electronics, particularly for hybrid cars that they use power electronics chips, they need to worry about that. But still, I would argue that the currents are small, right? Right? But it's a very important question that you raised. Yes.
So when you're doing the electrical test on
Yeah.
wafer,
Yeah.
how do you do it in such a large scale? Do you have like camera that goes through every single die?
Based on the Silicon Run that I saw, Silicon Run, I think one talks about it in the end, and 2 talks about it in the beginning.
Yeah.
I think they have like an automated process
Yes.
when the robot picks up the chip and then they put it on the well, actually they don't pick it up. They test like they have like a whole bunch of needle going through the electrical contacts, and then they test like that, and then they go to the next one, and so on. But before they do that, they're gonna have to grow that passivation layer so that you don't hurt the remaining of the circuits
Exactly.
on that way.
And also, initially they scan it optically, okay? And then they look also for thermal variation optically, right? And they do go through some trials and run initially to make sure that the reliability tests are acceptable for vibration, force, and other forces, other parameters that the chips could face, right? But overall, I think what he raised was really important. Passivation approach is really important for some of this because you're adding another layer which is neutral here, but it could withstand the vibration force and thermal variations and things like that without changing the functionality of the chip, right? Yeah. What's it?
So during that testing, like I'm assuming these because in our lab when we were testing our devices, everything got scratched, right? So do they have a method of not scratching theirs? Because I'm guessing that's really.
That's what the passivation layer is for.
Yeah.
So when that's applied.
Yeah, so that's why you grow. It's kind of thick. It's not like a thin one. It's kind of
Exactly.
So it
thick.
doesn't go through anything.
So yes, and they leave the contacts open though.
So the project that Justin is working on, particularly. You probably saw bits and pieces of that when you visited our lab. So we work on these ingestible devices that are very complex in terms of the development. And we haven't even gotten into the in vivo testing of this because we're just trying to understand how the whole composite works. And then the next step is to use it in a pig and an animal and see how that functions. But my point here is that he needs to make its own package for his devices. And he uses a polymeric material to encapsulate the sensors and electronics into a sort of a compact form that could actually travel through this gastrointestinal tract, right? Now that polymeric material better what? Stand the changes in pH, right? Because the pH changes as this capsule travels. The second thing is permeability, right? How much water is this going to take? How much other stuff is going to take? Because this is, at the end of the day, it's a sponge, right? It's not a very solid material. So any diffusion of any of these molecules or any of stuff in the media of the GI tract could penetrate through the thickness of that polymer and could change the functionality of that sensor. So these are the issues we need to face for that packaging application, right? So this is what I was saying. Even though we have a well-developed recipe now for electronics, when we go into the sensors and other forms of sensor, systems, the challenges change. Well done. Good job. Good job. Okay, let's go to the next group. Last but not least. This is a special day. We have two groups back to back. Aha! The very first examples of MEMS devices. Huh? Did you have fun? You did. One more. Yeah. There you go. Okay, start.
So, hi, we're Hussein, Max, and Nigel, and we're going to be talking about a couple examples of traditional MEMS devices, the gyroscope and the accelerometer. So to start, I'm just going to give a very brief overview of MEMS. MEMS stands for micro electromechanical systems, which, as the name implies, combines electronic and mechanical components into microscale systems. So, MEMS devices generally have components that fit into four categories, being microstructures, microsensors, microelectronics, and microactuators. So microstructures, as you would imagine, is the overall structure of the device, including general shapes like valleys and hills, as well as the actual mechanical components that will be manipulated later on. Microsensors are sensors that can detect a change in the surroundings or an input signal of some sort and communicate this to the microelectronics via some sort of signal. The microelectronics are then able to process the signal and accordingly activate the microactuators, which then manipulate the microstructure. So all four of them work in a very intertwined manner. So in MEMS actuation, there are four general types that we like to focus on: electrostatic, electrothermal, electromagnetic, and piezoelectric. There is a fifth that is considered, which is electrochemical, but since this field is very, very new, we're not going to touch on it today as it's not very widely used. So the first method is electrostatic actuation, which, as the name implies, takes advantage of electrostatic forces in order to create movement and force. So the very simple example is by taking a capacitor, you can generate an electric field or an attractive force in order to generate force and move the mechanical systems. The very simple example here is if we were to put a capacitor plate on top of the substrate as well as one on top of the suspended mass and apply an input voltage to charge the capacitor, they will have an attractive force between each other which will pull the suspended mass down towards the substrate and create mechanical movement and force. Due to the capacitor design, this has a very low current consumption, but could require a very high driving voltage in order to put up the mass. in order to generate sufficient force. Due to its reliance on an electrical system, this has a very fast response and is the most commonly used method of MEMS actuation. The second method is very similar, is electromagnetic actuation. Rather than taking advantage of electric fields and electric forces with a capacitor, we instead can use like a wire coil, or so we can use like a wire coil in order to generate a magnetic field. In conjunction with a magnet or magnetic material, we can generate force and motion similar to that of the previous example. Since we're now using a wire instead of capacitor, this has higher current consumption with a relatively lower driving force, but still has an extremely fast response. However, due to the large form factor of electromagnetic actuation in current iterations, this is much less commonly used than electrostatic actuation. The next main method of actuation that we use is electrothermal actuation, which, as the name implies, uses thermal heating effects in order to generate movement. So the basic premise is to use selective resistive heating in order to heat certain parts of the structure more than others and create a sort of movement. For example, if we were to take the example in the top left, where we have a thinner arm and a thicker arm and heat them accordingly, the thinner arm will, because of higher resistance, will heat up more and will heat up more than the cold arm and expand more than that of the cold arm, generating a curve towards the cold arm. A similar example would be the top right example, where we have two arms, and when heating them up, they expand, pushing the apex outwards. So this can generate a very high driving force and displacement due to thermal effects and expansion being a very powerful method, with a relatively low driving voltage through resistive heating. However, due to resistive heating and not using electric components, this has a much slower response time, but is capable of very high displacement and force. The final method that I'll be talking about is piezoelectric actuation. So piezoelectric actuation uses the same concept as piezoelectric sensing, where the displacement in a crystal is correlated to the voltage across the crystal. So generally, while we use this in a sensor where compressing the crystal generates our voltage and we can sense that, we can actually use the other way around, where we can apply voltage across the crystal, which encourages it to bend. This generates an actual movement, which allows the overall structure to curl in the direction that we want to. So compared to other methods, this method suffers in terms of not being able to produce as much displacement, but can generate extremely high forces.
Very good. Wow.
Yeah, I'm going to talk about fabrication. The fabrication of MEMS is pretty similar to our have learned stuff on integrated circuit. It has many same steps like oxidation or spurting that we have used in our lab before. And the main three steps to do the fabrication is bulk micromachining, surface micromachining, and high aspect ratio micromachining, also called HARM. First, the bulk micromachining. We have learned this so many times in our lab and in our class. This is the oldest way to do it.
See, now it's all coming together,
yeah.
right?
Yeah,
making
right.
sense. Yeah, hallelujah.
This is the oldest micromachining technology, and we just soak our substrate in the chemical and do the micromachining and etching step. Of course, it will cause chemical waste. And then the surface micromachining, this is the stuff that we're learning these days. It's just first we deposit a layer of oxide, and then the substrate we need to build, and then remove the oxide under the substrate, and then our surface micromachining is finished. It has precise dimension control on the vertical and horizon. And so it can create a large variety of structures, but the micromachining property of the surface micromachining is we have to test them after we have finished them, because they are unknown.
Yes.
And last one is the high aspect ratio micromachining. Of course, we have learned this before.
The commonly used we have used. You learn the Liga, you learn the reactive ion exchange.
Right.
Yes.
It's just use what we have learned beforehand because it can cause a very deep etching into our substrate. And that's it for high aspect ratio vector machining.
So can you go back to your previous slide? I just want to point this out,
Sure.
and you explained it so nicely. What does surface micromachining look like? Yekta, you're napping them. Surface micromachining. He says you put layer down, you subtract layer. Well, this is what you did in this class. This is how you make transistors, with the exception of, well, in some cases here we don't do the doping, but in some cases we do. So my point here is that surface micromachining is the process by which you could make both sensors and electronics, right?
Yeah.
You could make MEMS and you could make electronics. And this is what is at the heart of what you have in a lot of your gadgets, from Fitbit to iPhone to tablets.
Such a basic idea.
Yes, that's right. Because the packaging is the same,
Yeah, right.
right?
Right.
With the slight changes,
Mm-hmm.
right? All the principles apply, but more importantly, you could make them all at the same time. Are you with me? You could make them all at the same time. In fact, there are foundries that you could sit in front of your computer. My colleague and good friend Pamela Abshar, some of you had courses with her. She sits in front of her computer, designs this, sends the layout, and then they make the electronics and sensors for her, and then she calls herself MEMS. And I said, no, my friend, you're not MEMS. I'm just teasing. Okay? But the bottom line here is the same thing, right? And they make it for her, it comes back, they do the tests in her lab, right? For the sophisticated designs that she does.
So is she married or not?
Of course she is. She's a system. She's a system person. I'm also a system person. So, okay, go ahead.
Okay, so now going to the gyroscope, which is our first of the two devices in MEMS. So these are sensors that measure rotational motion on a particular axis. This device consists of a resonating mass that's mounted on a frame and can sense like angular velocity if it's rotating. And there's many different types, but the main idea of a gyroscope is like when there's rotation, this mass in its frame is shifted as the rotations per second change. Wait, go back. So you can sort of see here, this is kind of like a schematic of it, and a little more of how it actually looks here. But this right here would be like your resonating mass in the frame that it mounts on. And then you have two other kind of like connectors that are put perpendicular to how this one moves. And that's kind of like how you get the X and Y axis, how they move. I'll go into it in a second of what these are, but these are Coriolis sense fingers. And what essentially these do is as this shifts around, you essentially have a capacitor here. And as they move, the capacitance changes since they get farther and closer. Because we know like it's dependent on its distance from each other. And you can take that and actually like measure its capacitance, and that's how you can tell like how much it moved from this rotation. So the Coriolis effect. Really quick to say, for example, if you had like a rotating platform, and you say you were like standing close to the center of it, and your speed is like relative to the ground, obviously. If you start to move towards the edge of it, you would notice that your rotational velocity would change. You guys probably would know this, but this is the like main principle of physics that's used for this device. So it's the same exact idea here. Like when it's on that chip, like as if like your phone is rotating, it's gyroscope. You have in turn on, but essentially it would do the same thing. This would shift around on the inside. So the capacitance changes in the order of like zeptofarads, extremely small. But with the signal being this small, it's really important to reduce the noise that comes into play. So like these sources of noise could be like temperature, which is a big one, package stress, external acceleration, and electrical noise. So since it's on the order of zeptofarads, like this is like what makes or breaks it pretty much in a lot of ways. So to fix this error, you can incorporate amplifiers and filters on the same die. The biggest aspect that affects the sensor, one is temperature. It causes a bias. So gyroscopes, you'll see a lot of them have a built-in temperature sensor, and this way you can read the temperature and adjust values correctly, like within your code, so the gyroscope is read correctly. Another important thing about gyroscopes, so if you're like trying to pick one for whatever your application is, sensitivity and range becomes a pretty important parameter to look at. So you kind of want to, obviously, if you're looking at like a record player that wants to spin extremely slow, but if you're looking at a spinning wheel, it's fast. Like you're gonna have a different some ranges to look at. So the sensitivity is measured in millivolts per angle or degree per second. So this is how much voltage changes given some angular velocity. So if a gyroscope has a sensitivity of like 30 millivolts per degree per second, and you have 300 millivolts of change in the output, then you rotate it 10 degrees per second. So you'll see as the sensitivity increases, the range decreases. And other types of gyroscopes are ring laser, fiber optic, quantum, and vibration gyroscopes, which are all like fields of research of their own, but obviously I can't go into 10 minutes. But. So accelerometers is another electromechanical sensor. Measures static or dynamic acceleration.
So Hussein, come up front, yeah. Okay? Explain it to us instead of looking at your computer, okay? Use this screen.
Oh, yeah.
Okay.
It's kind of okay.
Yeah. Don't look into that because we want to see you. So
yeah. Okay. So the idea is to detect acceleration and convert it into an electrical signal. Two types of accelerometers: variable capacitive and piezoresistive. I can't remember.
Piezoresistive.
Piezoresistive. Acceleration would be like gravity, it's a constant force that's always acting, and dynamic would be like non-uniform, so like vibration shock, so like in crash testing for cars, that would be used. Variable capacitive accelerometers are low impedance output high sensitivity devices used for like static acceleration measurements. So these are DC coupled, so they're best for measuring low frequency vibration and steady state acceleration. They suffer from poor signal to noise ratio. Piezoresistive.
Now that's a really big deal. As you mentioned, there's different sources of noise.
Yeah.
The signal to noise ratio is at the heart of a lot of these devices, accelerometers, gyroscopes. Yeah.
Piezoresistive accelerometers these are high impedance output and low sensitivity. So these, like I said, are used in shock vibration applications as well. So these have a higher bandwidth, so they can be used for short duration, high frequency shock events. Structure of this device. So VC accelerometers, they consist of some proof mass suspended between two parallel plates, and the mass is then attached to like a ring frame. So when you have it set up like this, you have like two air gap capacitors, an upper plate, mass, lower plate, and then when some acceleration is applied, this mass shifts its position, and then the plates will change the capacitance, which will be proportional to the acceleration applied. So maybe kind of the same thing, but kind of like right here, how you have like this would be the upper one, lower one. And this is kind of like your structure that's it's like a flexure, so it can bend and move, and like how much it like vibrates is pretty much how you can tell like how much acceleration is being applied. Now for the PR accelerometer, piezoresistive, these also have flexures in them as well, between an upper wafer and a lower wafer. So So when you have a vibration detected, the flexures in the middle will bend and cause a change in resistance that's proportional to the flat acceleration. So the middle wafer is bonded to the upper and lower one with a glass bond, and the sensing elements of this device are used with a Wheatstone bridge, and this configuration uses those two resistors. And when you have this these flexures bending, you have two resistors that are increasing and two that are decreasing at a time. So these are referred to as tension and compression gauges. So the difference in voltage of these output lines are proportional to the excitation of voltage applied. So
That's right.
And it's sort of I just included this because I want to see it later, but
Very nice.
sort of how the applications where you would use them. So high impact and extreme shock ones, and we only use these as
This is your last slide?
No. Actually, just
almost, I think it's
Oh, this is the last
yeah.
slide. Okay.
Actually, Stanko saying that leave the two easier part for me. For application, there are maps everywhere in our normal life. Yeah,
I call it quiet revolution.
Okay. Yeah.
Right? Because it's no longer the future. Our lives are so dependent on it.
Yeah, because when I Google the Maps application, the first thing I saw is the Philips homepage. That it introduced so many kinds of his product that use maps in it, like the maps inkjet printhead, the CMOS, and so on. There's a page of 16 different kind of product that use maps, and it's also used in airbags, the computer disk, drive heads, and projection display chip, blood pressure sensors. It's just everywhere. Thank you.
Good job. Excellent. Excellent. Questions? Go ahead.
In the gyroscope, you mentioned there's an oscillating mass. What starts it oscillating? Is that some other input, or is it just somehow naturally?
gravity. Like as you just turn your phone, this mass that's suspended just moves around.
Okay.
Yeah.
Sometimes they also apply a small signal to have a constant vibration at a very, very small level. Yeah, it depends. I mean, there are different tricks that talking about the challenges of the circuitry, to make sure that to cut down, as we were talking about, the signal to noise ratio. I'm sorry, the raise it, not cutting down the noise. Yeah. First of all, I have to tell you, all three of you did really well. We have done something like this in the past. You guys have done one of the best in such a short time. So kudos to you. I so appreciate the fundamentals. I so appreciated the techniques of the processing and development, and very much the concepts of the application. So well done, really, well done. This is the best way we were able to finish this group presentations. Any other questions? Any questions? Let me tell you this. This morning I was having this, my other half and I, we get into discussions. She's a microbiologist, I'm an engineer, so we often get into this. So she was telling me all about metaverse. You guys are familiar with metaverse? Who is into metaverse? Huh? Well, he changed the company to Meta.
Yeah.
Okay? But Meta is now not your generation, the younger generation in elementary schools are so into this metaverse, that they're now having their birthday parties, their gatherings in this meta world, okay? Which is frightening me, right? And apparently this 2 years of pandemic and the Zoom Live accelerated this hugely. There was a long article in New York Times this morning about this metaverse. People are now getting married in metaverse. It's crazy. So the bottom line here is this virtual reality, this goggles, the guy who gave us money to build this computer science building, he was a dropout, but he made multi-billion. It should not be a good model for you. These things happen 1 in a million, okay? But the bottom line here is, he sold the company, he's no longer the owner. But I remember when I had a discussion with him 7 or 8 years ago when he was ready to give us the money, he was very interested in the marriage of MEMS devices with virtual reality. Okay? And God knows what he's doing right now. Now, my former students who work in Facebook Reality Labs in Seattle, they all working on wearable devices. And they don't tell me what they do. Okay? So, why this relation between virtual reality and sensors? Why? Why do you think this is becoming?
To build a connection.
To build a connection, because once you wear this, you're a human, so you feel things, right? You could hear things, right? You could see things, but you cannot smell it, and you cannot touch it, right? So the sensors that they need to make to allow this metaverse world to smell and to touch is all MEMS. Okay?
Like smell-o-vision?
Absolutely. Absolutely. Because when you walk into a garden in this virtual reality, you want to be able to smell the flowers. Right? So that sensing through artificial intelligence and machine learning and all of this stuff that I don't know anything about, they come into play. But more importantly, I would say, this sense of touch. And tactile sensing. That's all MEMS. Okay? So accelerometers, gyroscopes, and a lot of this movement which previously was used for robotics, for remote assisted robotics work, they're going to all come together into this metaverse. Does it make sense? She was actually kind of impressed when I explained this to her. But because of microbiologists, they don't know. But the bottom line here is this is actually, as you said, they're everywhere, but there's a new phase of this that is starting to surface, right? So I wanted to share that with you. Well done. Good job. Justin, can you pull up the screen? And I just want to go over a couple of things before we let everyone go. Excuse me? Yes, I will. So, we have lab report 2 that I hope you're almost getting to the end of it. We have the last homework, and we have the homework for today, okay, for these 2 group presentations. So I'm giving you an extension until Wednesday is the exam. So Monday afternoon at 5 p.m. is the absolute deadline. Okay?
For all three.
For all 3.
Wow. I was expecting midnight. I would have been happy with midnight.
Wait, so what is this homework assigned?
Today, right now.
Okay.
Yeah. Right. So there would be a compromise, right?
Okay.
Yeah.
I'm not going to give you the whole week because your exam is coming up.
Is it only group presentation homework?
Yes. Yeah. And the last homework that you have already done.
Okay.
Okay? Is that good?
Thank
Yeah?
you.
You feel good? Okay. All right. So let's get this out of the way so there will be no worry. But if you don't do a good job in your lab report 2, if you don't show me that you were able to graph things, discuss things, explain things, turn this into a professional lab report that you could be proud of later on, we would be much stricter than before in grading this, and I promise you that, okay? We're not going to be as nice as we were last time, okay?
Which time?
For lab report 1.
We haven't gotten anything back.
the grade.
This will be, I'm posting it, yeah.
Huh?
I'm gonna send it out today. I'm done. Yeah. We'll talk.
Okay. First of all, I have to tell you, I so much enjoy this class. I enjoy all of you. I think this is one of the best 416 classes I've had. So kudos to you. I hope you learn. I hope you would be able to take some of these materials and apply it in your next phase, whether you want to continue for graduate school or you want to go get a job in industry or just in general, okay? One thing that grabbed my attention when I was editing your CVs last weekend, the 12 of you who submitted your CVs. First of all, I was very impressed. I thought you all did a good job, but there were some commonalities, there's some common problems that I tried to point out. It's really important to pay attention to the format of your CV. And this is the first time I'm actually doing this in this class, because I think you need to be aware of the formatting. Okay, the content was good. The formatting had a little bit of a difficulty problem. So make sure that you address those things. Secondly, the other thing that I was going to say is a number of you have approached me to potentially do a semester of independent study. So I want to tell those individuals, once you're done with the class, your grade is given, then come and contact me after the holidays, okay? And then we can talk about this. And certainly I'm all open to provide the opportunity for those select individuals to come and work with us for at least a semester and hopefully gain more experience. Second thing, the next issue that I was going to bring up, the final exam on Wednesday. Basically, there would be no surprises for anyone, hopefully. The format is exactly the same as your midterm, okay? We will start with questions that you need to tell me if they are true or false and why, okay? So read them very carefully. Don't rush them, okay? Understand, we're not trying to trick you, okay? So understand what I'm asking and then explain why this is true and why this is false, okay? And then we have problems that they hopefully resemble the homework problems that you have had throughout the semester, okay? The final exam is going to be comprehensive. It's going to include everything. However, you learn about doping, you learn about mainly diffusion, doping, as well as the ion implantation. You learn about thermal oxidation, how to predict the growth of the film in the thermal oxidation system. You learn about passive and active devices, how to test them. You had a lecture on those. You have had a series of group activities that we covered. What is going on?
We're in the same lab group, and we just made a funny joke about having more time on the extension or the project.
Okay, all right. I like people, when I see them laugh, but not, you're talking about the serious stuff. So you need to cover those group activities as well and go over the concepts. But I have to tell you, one of the things that I will try to test you on is to see how you can approach a design problem, okay? So the design problem you're going to have in the exam, or one or two, they would be harder than the midterm. They would be more comprehensive. So don't rush. Read through it. Understand what I'm asking. And then try to show me how to approach this, okay? And never leave anything incomplete. You're going to have 2 hours, same format as the midterm, 1 sheet, front and back, that you could bring with you, and no other sources of information, hopefully, and you're going to have a full 2 hours here at 8 a.m. We finish at 10 sharp. And so do your best. What we're going to do, yes?
I was just gonna ask, since we have like 2 hours now, is the exam gonna be like longer, like more questions?
A little bit. A little bit, yeah. We try to be fair. I know the midterm, a lot of you were unhappy about the length of the exam. That's often the case here. I show you how you did in comparison to the previous class. However, yes, it's going to be a little bit longer. It's 2 hours, but not significant. What we're going to do, I'm so surprised about the lab report. Yeah. First of all, so let me finish this before I get to the next topic. We are going to grade everything and evaluate everyone's participation and effort in the class. What I told you in the first lecture, I paid very close attention to those who regularly came to class, participated in discussions. I look at how you did in the homework. Homework matters to me a lot. I look at your lab report, and of course your exams. And then I see how the whole class did. And then we try to arrange a system that is fair based on overall performance of everyone in the class and your individual performance. And that's how I will assign the final grade. Okay? Most probably, we should be done by Monday after the exam. So not this Monday that's coming up, the Monday after your exam. That's when I'm going to assign the grades. And then Justin and Jinjin, they're going to have at least 3 to 4 hour office hours the Tuesday after that in our lab for anyone who wants to come to see the problems, how they did, if they have any concerns, and we're going to go over them with you if you wish to do so. Okay? But then you're done. We're done before 22nd. Okay? So the 21st is when we finish everything, and we try to answer any questions that you may have. What I told you at the beginning of the semester, and often have to educate my colleagues, this is the most costly, involved laboratory/lecture course in this college, by far. Okay? The amount of money, time, materials, supplies, planning that go into teaching you how this whole world of IC fabrication and devices work is really unbelievably fantastic, in my opinion. I have buddies at MIT, at Berkeley, at Stanford, at Michigan, and often when we share notes, they're always in awe when they hear about what we do in this class. So you should be very proud of the fact that you have been part of this. I'm also immensely thankful to these two individuals. So let's give them a big round of applause. I think you agree with me, they did a fantastic job, even though every now and then they slip. I'm also annoyed of the fact that the Fab Lab staff didn't pay attention to those two very important issues. One was to emphasize how many measurements you were supposed to do for the first lab report. And then, of course, the fact that they use a different doping type wafer, that you ended up not getting your hard work being tested. So I apologize for that, but I also want to emphasize again, things like this happen in a class like this. No matter how organized we are, no matter how careful we are, every now and then things happen and we need to address them. So I think I covered everything. It's really important, honestly, for you to spend 15 minutes and do the course evaluation. Please do that. This is your responsibility for the next generation of the students who are going to take this class. Take the evaluation seriously, give us your feedback, Your feedback counts. I read all of them. So please do that. I think that's your responsibility as a student in this course and any other classes that you have to take your evaluation very seriously. Any questions? Did I cover everything? Did I miss anything?
I think we got everything. Just announced the review session. We were going to do it on the reading day, 2 p.m., just for an hour and a half.
Absolutely. And it's going to be where?
We'll do it here because it's a reading day. We can do it in this room.
Do you have to reserve it?
I have to reserve it.
Well, do it right away.
Yeah.
Do it right away and then let everyone know later. Okay? Yes.
A small question about the review session. Is that going to only talk about the final exam or the lab report is also covered?
Everything.
I mean, yeah, the lab report will be due, but we can discuss it. Yeah.
Yeah, you could discuss it, but the focus of the review session is on the exam. Yeah. But if you have any questions about the lab report, I mean, your lab report is already due
Monday.
on Monday.
Yeah.
Yeah. This is after that. Yeah.
In addition to
For lab reports. Before it's due.
office hour, the lab report's due Monday. You want an office hour for the lab report?
You could just send him an email and go see him.
Yeah,
Okay.
I have been.
Okay, well, then just do it again. Yes.
When we're done talking about the final exam, I do have some questions about the lab, if that's okay.
After you done what?
After we're like having this discussion, I have some questions about the lab.
Okay.
If like I can ask them.
Yeah, no problem. Yeah, absolutely. Any other questions? No other questions? Best of luck, and I hope to see all of you, and good luck in your exams, and best wishes for the holiday. Okay. Well done. Thank you. So you want to come up front?
Oh,
Ask?
that's the last one.
What?
Yeah, that was the issue.
Ginger.
Maybe your name is fine. Yeah. The solution is, we were waiting for